Hello, we're the Stony Brook Robotics team, and we would like to present this year's URC rover, Tetra, the terrestrial and extraterrestrial research apparatus.
Our mechanical team has four main subsystems: chassis, suspension, arm, and sides. The lightweight sheet metal chassis serves as our suspension's mounting support, as well as our electrical housing. An opaque plastic cover and fans with dust-proof shielding provide a safe and cool environment for the electronics.
Our rover utilizes a passive differential rocker suspension with an additional shock absorption system. This allows the rover to navigate over obstacles larger than the diameter of its 12.5-inch wheels. Additionally, the freely rotating rocker assemblies are able to conform to the terrain, increasing the traction of the treads by maximizing the wheel's contact with the ground. The rover has two rocker assemblies connected via a differential linkage. Each leg can rotate independently from its rocker assembly. The angle between the legs on either side ranges from 110 to 150 degrees. This is crucial to our shock absorption system, which utilizes compression springs to hold the legs closer together while allowing them to spread apart during a direct drop or impact. Our rover's arm has 6 degrees of freedom. The arm utilizes a linear actuator and a combination of MX106 and AX12 servo motors to move the upper arm and forearm respectively. A pulley system is used to allow for the bulk of its weight to be closer to the mounting base for better stability. The arm was designed for high strength while only weighing in at 5 pounds. The rover's hand attachment connects to the arm via a differential wrist, and the worm gear is used to open and close the fingers to ensure a tight grip.
This year, the electrical team minimized the amount of hardware necessary for our rover to operate. Prototyping tools, like our circuit board printer, were used to quickly make and test any hardware needed. We have been working on embedded software to integrate our power, controls, and sensors subsystems to the mechanical and software aspects of our rover. Our custom-designed power board allows us to efficiently power the rest of our boards, including the Jetson and servos actuating the arm, while also monitoring power consumption by different modules to ensure proper operation of the rover. Our motor control board uses an H-bridge circuit to control the motion of Tetra. All of our boards communicate via an I2C bus, and since the Jetson is connected to the same bus, data can be quickly transferred from the base station to its destination modules. Tetra's arm uses a customized connector board to easily remove the arm when changing between URC missions.
The software design was built with an emphasis on modularity and simplicity. The overall design is divided into two main components: the base station and our onboard computer, the Jetson. On the base station, the internal communication subsystem was developed using the 0MQ distributed messaging library to create a lightweight and efficient message passing scheme. Additionally, the GUI subsystem displays a GPS map and various information from an inertial measurement unit, IMU, using tkinter, Python library. Furthermore, it displays multiple video streams and data plots from the sine sensor array. The external communication subsystem serves as our means of communication between the rover and the base station. It utilizes two Ubiquiti Rocket M2 base stations with omnidirectional antennas to create a point-to-point network on the 2.4 GHz Wi-Fi band for non-line-of-sight communication. On the rover, the Jetson runs two subsystems. A vision subsystem utilizes a Z stereo camera with a neural network based in PyTorch to be able to track the tennis balls used in the autonomous traversal mission. The autonomous navigation subsystem is a multi-part algorithm which collects data from both the Z and the IMU. We constructed a simultaneous localization and mapping SLAM algorithm to generate tracking points, which becomes the basis for our A-star pathfinding. This output is then fed into a navigation algorithm.
Our goal in the science mission is to determine the habitability of the landing site locality through clues such as the presence of liquid water, either in the past or at the time of landing, and atmospheric conditions, as well as through the identification of potential biosignatures. Atmospheric conditions will be measured with a suite of atmospheric sensors that sense temperature, relative humidity, UV intensity, atmospheric pressure, atmospheric oxygen levels, volatile organic compounds, carbon dioxide, and carbon monoxide. The combination of these measurements will tell us if liquid water is stable at surface conditions or is present in the atmosphere, if life could potentially exist in the sampling location, and if photosynthesis or other O2 generating processes are active.
The past presence of liquid water will be investigated through mineralogical characterization of both regolith and whole rock samples at the landing site locality. This will be performed with a Raman spectrometer and built by our team. We will be targeting carbonates, sulfates, and organic carbon. These minerals have been selected because they precipitate from liquid water and are subsequently preserved in aridifying environments. Organic materials could be a sign of past organic life forms. Thus, Raman spectroscopy is capable of identifying both past habitable environments and trace biosignatures in the Martian rock record.